Okay, so last time we talked about um, exponential functions, and you got to see what they look like, and you got to graph exponential functions, right? Um, One thing I didn't mention last time was, remember how I said this number E is named after the mathematician Euler? So here's something interesting, like a little trivia fact for you guys about Euler. Um, Euler was a prolific mathematician. He discovered and came up with so many things. There is E named after him. There's Euler's method. There's Euler's formula. There's Euler's this. There's Euler's that. And it got to a point where everything was being named after Euler. So the math and science community decided to stop naming things after him, and they started to name them after the second person who also came up with it independently, right? Like the second runner-up. So, fun fact about Euler, if you're ever on Jeopardy and that comes up, you have to give me on-air credit, like on the spot. Yes? Okay, cool. All right. So personal favorite of mine, that boy Euler. Pet peeve, so many people pronounce his name Euler. Not Euler, it's Euler. All right? Okay. All right. So exponential functions have many applications, right? A myriad, a plethora of applications. One of the most common that everybody comes into contact with is compound interest. And you've probably seen this formula before. This is the formula for compound interest. So what you have is A is your final amount equal to P, which is the principal, not Miss Howard. That's the money that you go to the bank with, right? To open up your account, initial investment. R is rate. T is time. And N is the number of times the bank pays you per year. Okay? So if you get interest paid, if the account is such that you get interest paid quarterly, that's 4 times a year. So N is 4. Okay? Now, the sister formula to that is the continuous compound interest formula, where A equals PE to the RT. And you only use this when you hear or read the word continuous or continuously. This means that the bank doesn't pay you once or twice or 4 times or 365 times. The bank is paying you continuously, every nanosecond of every year. Okay? All right. So how do we get from that formula to this formula, right? Let's just see. This is what we started with. And remember what I said in the last section where E came from. E, right, comes from this term 1 plus 1 over x to the x. And look at how you have that same thing here. 1 plus something over n to the n, right? Tell me that's not the same thing. 1 plus 1 over n to the n. And as n approaches infinity, n is the number of times that you're getting paid. If you're getting paid continuously every nanosecond of every year, how many times a year is that? Infinite number of times. So as n approaches infinity, that whole thing becomes an E. And so now I have A equals P e to the t, and then there is some math where, you know, the r goes over there. So do you see how that transforms into the other? Okay. All right. Let's do some examples here. Mrs. Drew invested $2,000 into an educational account for her daughter when she was an infant. The account has a 5% interest rate. If she does not make any other deposits or withdrawals, what will be the balance after 18 years if the interest is compounded quarterly? Okay, so let's see what we got here. She invests $2,000. That's the principal. The rate is 5%, which in decimal is 0.05. We want to see how much she's making in 18 years. That's the T. And if interest is paid quarterly, that means 4 times a year, so N is 4. So we say A is P, 1 plus R over N to the NT. That's 2,000. 1 plus 0.05 over 4. 4 times 18. You plug it all in, and it gets you $4,891.84. Okay? All right, so this is Precalc Honors, and we're dealing with money. So it's up to you to know to round to 2 decimal places and round properly, right? You can't be off by a penny. Can you imagine if all the banks were off by a penny for all their customers? Oh my God, the havoc, right?
Save the government a lot of money.
That's a lot of money. I mean, the whole GameStop scenario, that's nothing, right?
Well, pennies are expensive to make. They cost
Yep.
more than a cent to make. So it saves the government
Absolutely.
because they don't have to make pennies.
Yep. Okay, so let's follow up. Mrs. Drew found an account that will pay 5% interest compounded continuously on her $2,000 educational investment. When will her investment triple? Okay. If it's compounded continuously, then I know I'm using the PERT formula. A is still 2,000. I'm sorry, P is still 2,000. R is 0.05. Now, though, I'm looking for when the investment will triple, so I'm looking for time. But what I want is for the final amount, A, to be 3 times the initial amount, 6,000, right? So 3 times 2,000, which is 6,000. Okay? So A, that's the final amount. We want that to be 6,000 equals to 2,000 e to the 0.05 t. Okay, now we're going to cancel out equal numbers of zeros. So 6 is 2 e to the 0.05 t. Divide by 2. So 3 is e to the 0.05 t. Okay, now here I have 3 equals to e to the power of something. Does anybody remember what we do here, Gavi?
Natural log.
Natural log. Take the ln of both sides. We're going to do this more formally in this chapter. But take the ln of both sides. So I get ln of 3 is equal to, the ln and e go away, 0.05 t. And now divide both sides by 0.05. So t is ln of 3 over 0.05. Notice I haven't plugged anything into my calculator yet. It's always best to work symbolically, like, or, with exact values until the very end, because carryover, rounding error, that's a big thing, especially with E's and LNs and all that good stuff. So now I plug this into my calculator and I get 21.972, right? So this is about 22 years. Okay, now you're gonna ask me, how do we know what to round to? Go with what is said in the problem. Sometimes it'll say to the nearest year. If not, just give both, okay? If nothing is specified, then you also won't lose points for not rounding to the correct place. Does that make sense? Let's get in the habit of doing 3 decimal places, only because calculus, usually goes for 3 decimal places. Okay, so those were investments. But in addition to investments, exponential functions apply to so many other things. For example, populations of people, animals, bacteria, amounts of radioactive material, okay? So for those, we have our general formulas. Now, these are the original formulas. Like, these are the, like the first ones that were made, and then bankers just modified them to, to use variables that they are comfortable with. So here we go. We have the formula for exponential growth or decay. All right, this is the notation your book uses. N equals N naught, 1 plus R to the T. This is N naught, N subscript 0. In math or science, when you have subscript 0, it means initial. Okay? So you can have N naught, I naught, V naught, F naught, whatever. 1 plus R to the T. This formula with the Y is more conventionally used. I don't know why your book does the N's. Like, if I ever meet the people who published this book, anyways, let's not go into that. Okay, right? That's the one that's normally used. That's the one I want to use, just so we have continuity for next year. Okay, and now if R is a growth rate, if something is increasing, then R is positive. And then if it's decreasing, R is negative. Okay, now you use that when things are, exponentially changing. In the case where something is continuously changing, right? You use the word continuous, then it's this. Y equals Y naught, e to the kt. And so look, because, math people just want to be cool, we use R for the non-continuous rate and K for the continuous rate. K for continuous, haha, I just came up with that, right? You don't even have to use, you'll just know. All right, so a state's population is declining at a rate of 2.6 people annually, right? Not continuously, so we don't have to use that formula. The state currently has a population of 11 million people. If the population continues to decline at this rate, what is the population going to be in 15 years? So let's write down what we have. First of all, the formula we're going to use is Y equals Y naught, 1 plus R to the T. So what we have here is R, 0.026. We have the initial amount, Y naught, 11 million. And time is 15. Okay, so we want Y in 15 years. So we say Y equals just 11. Don't put the whole million in there, but keep in mind that your numbers are in the millions. Now, it's declining, right? That means here it's going to be 1 minus 0.026 to the power of 15. Okay, so this is because it's declining. And then you put it into your calculator. Y is 7.4. So there are going to be 7.4 million people in 15 years. Okay.
Can you write out the full number and just say that rather than 7.4 million?
You can, but I always, you're going to be writing like a whole bunch of zeros. And what if you mess up because you're under stress or you're rushing and you do one extra or one less zero, right? So always be careful about that. Okay, next. Okay, these decay problems are my favorite. All right, they are just my favorite. Maybe it's a physics thing. I don't know, but they're just my favorite. Okay. Or maybe because radioactive decay was discovered by Marie Curie, like, woman scientist. Who knows? I wonder if that has anything to do with it. Okay, so uranium-235. This is an isotope of uranium. Has a half-life of 704 million years. What does it mean it has a half-life? That means if you have this much uranium and the half-life is 704 million years, in 704 million years, half of this will have decayed. In another 704 million years, half of what remains will have decayed. In another 704 million, half of that, until eventually it all decays. That's what half-life means. So the question asks to write a modeling equation for the exponential decay of uranium. All right, so part A, we're going to do that here. Okay, the formula for radioactive decay, right, for half-life, we use the continuous formula. Okay, so y equals y naught e to the kt. So let's talk about what half-life means. Half-life means at t equals 704 million, right? Your y, the final amount, is going to be half the initial amount. Yeah? So here, y is going to be half of y naught equal to y naught e to the k times 704 million, but we eliminate the million. So now this goes away. So I have half equal to e to the 704k. Take the ln of both sides. So I get ln of 1/2 equals to 704k. And so what's k? Divide by 704. K is ln of 1/2 over 704. Those of you taking chemistry, if you do decay, right, half-life, have you guys done half-life in chemistry? They just give you the formula for K equals ln of 1/2 over T or something, right? That's because they did all the math for you and then they just give you that formula, but this is where it comes from. So K is, here, I'll write it here, negative 0.000984. And I went to a whole bunch of decimal places It's wise to do that for k. Get some numbers, don't just stop at the zeros. So now you put that into your equation, so y equals y naught e to the negative 0.000984 t. That is the modeling equation. Okay. All right, that's usually the biggest part of the solution. Yeah, Ezra.
Wouldn't because we know the t, wouldn't we multiply that and just leave it?
That is actually a very good question. Thank you for reminding me. So when you write a modeling equation, you need to have two variables in your equation. So you want to have a y and a t as variables in your equation, right? That's the modeling equation. And then you're going to use this to find initial or final amounts at different times, right? So when you're asked for a model, always, 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 you need a dependent and an independent variable as variables. That's an important point. Thank you for telling me. Thank you for reminding me. Okay, so usually, like I said, this is the longest part in these solutions, and then afterwards it's usually just plugging in numbers, right? The follow-up questions. Elon?
So the 704 that we divided ln of 1/2. So did you plug in 7.4 million or just 704?
Just 704.
So does that
then,
not affect?
No, and then I just assume that my t is always going to be in millions. Yeah. All right. Next.
What about if like, you're given thousands? Then would you keep it in thousands or hundreds, keep it in hundreds?
You usually don't, because if the half-life is in 704 million years, then in a thousand years compared to that is
No, I'm saying if you have a different element has a half-life of 100 years,
exactly.
you'd use it. Okay.
Yeah. Okay, so B, how many grams of uranium-235 will remain after 2 million years? So now T is 2 million. If you start with 300, y naught is 300, right? So we plug it in, y equals 300 e to the negative 0.000984 times 2, because we're doing everything in terms of a million. Y is 299.410 grams. So again, if you're not told how to round, just go to 3 decimal places, especially for quantities of weight like this. And please don't forget units. Haley.
Wait, I'm confused because it's 2 million. So
before
do you see what
yes, before 2, it was 704 million, right? But in our equation, what did we put? We just put 704. And we're just assuming that all our times are in terms of millions of years. Yeah. Okay, and then, so look, 2 million years later, right? Look at this. I started out with 300 grams. 2 million years later, I have 299.4 grams left. Look at what a slow process this is, right? Okay, and then always, be mindful of that. Say, okay, 704 million years, half of it should have gone. 2 million is like a blink of an eye. Does it make sense that that's what my answer is? It should make sense to you because you guys are all analytically brilliant people. So it should make sense to you in your mind. Okay. Part C says, use your model to estimate when 200 grams will remain if you start with 300. So let's think about this for a minute. You start with 300. You're going to have 200. That's not quite a half, but it's close. So if it's 704 million years to get to a half, right? Think about, it's going to be hundreds of millions of years, right? Okay. All right. So y is 200 and y naught is 300. So we're going to get, our equation is going to be 200 equal to 300 e to the negative 0.000984 t. These go away. Divide by 3. So I get 2/3 equals to e, that fabulous number t. Let's take ln of both sides. I get, this goes away, ln of 2/3 is equal to negative 0.30984 t. So t is ln of 2/3 divided by that number, and t is 412.06. So this took roughly 412 million years. Does that make sense to you? Right? Is that what we kind of predicted? Yeah? 2/3 of, not 2/3 will remain. So, it won't quite be half of the 704. One other thing before I take your question, Gabi. Here, we got k to be negative blah, blah, blah. Did we expect for k to be negative? Why would we expect for k to be negative? Eliana?
Because it's decay.
Precisely. Okay, so again, another way to keep checking yourself as you go along. Okay, like debugging your work almost. Okay, Gavi, you had a question?